So next up we have Arjen, who's going to talk about local sharpening and his software lock scale, which was mentioned earlier today as well. Thank you.
Thanks, Martin. Thanks for the organizers for inviting me to present what we do on map sharpening. Tom has mentioned this already. I'm sure that Paul will mention it again. This one essential step in the process when you want to go from your map to a model. If you have, or if you are in the lucky situation that you have a map in which your resolution is completely isotropic, you can stretch your legs and take a nap for the next 30 minutes. If it's not, maybe it's worth to pay attention. So what we are trying to do is to address a problem that's very common in 3D reconstructions using cryo-EM, that you have a map in which your resolution varies often drastically. In this case, it's quite extreme, so we have parts in the map that range from around 8 angstrom to almost 3 angstrom in the core. And if you think about what this actually means, if you look at such a structure at these particular resolutions superimposed on all parts of the structure, if we would have a 9 angstrom map, that would look something like this. If we would have a 5 angstrom map, we could already start to see helices, or the pitch of the helix appearing. If we would have resolutions that are better than 5 angstrom, we could start seeing better strands separating. And if we are much better than this, we can even start to see bulky sidechains appearing. And if all of this is in one single map, then you can imagine that if you use a protocol in which you try to filter this map based on one FSC curve that you have determined for the entire structure, may not be the most plausible way to do this. So if we have such a map and we look at one region of this, for example, at one high resolution region here, which you see in section through this map, this definitely requires sharpening in order to reveal the detail that this map actually contains in terms of information. But different parts of the map maybe will require different procedures for filtering. And you can do this, so we came up with a way to do this, but there are many others. This actually has been introduced by the authors of Blockrush initially. So what you can do is, if you have a map and you want to determine resolution locally, you can do this by localized Fourier correlation. So if you have a signal, you can sample that signal in a rolling window, and you can use an appropriate apodization function to get rid of edge artifacts. And then basically you can just calculate an FSC between these windows, and you can do this in a local fashion, so you can move in 3D through your map in a cube-like structure that you apply an apodization function to, and you calculate the FSC at each position. You determine the resolution, and then you use one or other criterion to determine the resolution at this position. And if you know this, then you can filter the map and assign the value of the voxel that you have in the center of that cube to a new map, and you basically generate a locally filtered map. Reliant can also do this, and there are many other tools. In Symposium you have monores, so there are other ways to do this. What does this mean? We basically now start from this original reconstruction. We apply sharpening to that map, so we get a sharpened map, which at some points in the map will probably be correctly sharpened, so we can see a lot of detail now. And then we apply a local filter to that map to basically filter off noise components where we have excessively sharpened, but keep information at high resolution where we have correctly sharpened. This is good, but it actually does not take care of varying contrast loss. So if you have a map in which resolution varies drastically, then probably also the sharpening should actually be adapted locally. And this is what we try to do. And that this can make sense, I'll try to illustrate by a simple example, a simple 2D example. So what you see here is an image over which we have laid a gradient where basically the amplitudes are locally scaled differently. And what you see in the middle is a detail of that image, and then you see a power spectrum of that image, and you see a radially averaged power spectrum of that image. And what you can do now is basically keep the phases of this image and substitute all the amplitudes with random noise. So that would give us an image in which we almost have no contrast anymore, because now basically our amplitude spectrum is completely flat over the entire frequency range, and you can also see that in the power spectrum here. But we still have the phase information from the image, so if we restore that contrast, we should be able to also restore the details that are in the image. We can do this with an exponential fall-off correction, so we can basically take the image, we can estimate an approximate fall-off, and apply that fall-off to our random amplitudes, and then you see that you're starting to restore contrast in that image. And you see here the two curves are always superimposed on each other. So this is the radial amplitude profile of the original image. You can do this slightly better by doing a reference-based fall-off correction, where you basically use a reference profile in resolution shells, and you impose the scaling of the power spectrum based on this profile, and then you see that you actually get much better contrast. But you still see that in this amplitude spectrum of the original image, you see many of these stripes occurring in the power spectrum, and these come from all the repetitive features that are in the image. And in this procedure, actually, we are not able to restore them correctly, so we actually only see very few of these features back. And that has to do with the fact that this amplitude profile is not constant over the entire image. So what we can do now is basically use a rolling window which we move over that image, and in that rolling window we do a reference-based fall-off correction and then assemble this into a final image. And you see this here. So this is one tile of the moving image that you see in this case. You see the image detail, and you see that now in the amplitude spectrum, we are, at least in some parts, we are able to reconstruct these repetitive features because we are able to resolve them better. And you can take this idea then and take this to 3D and apply it to EM maps. The question is whether that is necessary. So if you look again at a map here that varies in local resolution, the question is, if we now estimate B factors in a local way, do they also vary across the map? You would intuitively say yes, but we of course have to check that. And you can do this in the very same way. So basically you move a cube across your density, and then for each of these cubes you produce a Guinea plot, so basically just the power spectrum, radially averaged power spectrum across that cube, and you estimate the B factor from this power spectrum. And then you can plot this back onto your map, and you see what is the average B factor in each density cube that you have chosen. You can see that this definitely varies across the map, and it also correlates nicely with the local resolution. These are some other examples that basically show the same features. If you have a map that is very isotropic in resolution, then you see that also your B factor obviously varies very little. So this is beta-galactosidase. You still see some parts where this is different. But the higher your resolution is, the better also is the goodness of fit of this Guinea estimation, simply because you have more data points over which you can fit the fall-off. If you then look at local resolution and you look at an atomic model, so if you have a map in which local resolution varies and you refine B factors against these maps, you can see that the B factors obviously correlate strongly with the local resolution in these maps. So these are just 3 examples. And on the right side, you see the models on which we have plotted the B factors in rainbow colors. So the idea is if you assume you have a model which you can use as a reference, then we can actually use this approach that I showed you in 2D and apply it directly to 3D. So the idea is the following. You have a 3D reconstruction, and you have some way of getting an atomic model which you can use to refine B factors of that atomic model. Then you can use this atomic model to scale your amplitudes, keeping the phases from your original reconstruction. And that will give you a scaled map that you can use to build an improved model. And you can use eventually this model in further refinement, maybe getting a better model that you can use again to iterate this procedure. But there is a limit to how far you can iterate this. So if you look at this schematically, what you do is the following. You have your original unfiltered, unsharpened reconstruction. And you now have a model map, so a Coulomb potential map that you have generated from your atomic model with the B factor distributions in that model. And then you're using the same rolling density windows. And basically, for each of these windows, you calculate the radially averaged power spectrum. And then you use your reference power spectrum to scale your experimental power spectrum. And this is the result of this procedure. So these cubes differ a little bit depending on the resolution of your map, but typically they're about 20 to 30 angstrom wide. And this is one of these unsharpened density cubes from your original map, and this is what happens if you sharpen this. And that's basically you move this through the entire 3D reconstruction. This is the result that you get. So if you have, this is RNA polymerase that has been scaled locally. This is our own structure, so I can show this. That is actually not very good in the parts that are at very low resolution. So you see that's a very noisy part, but if you scale locally, then you're actually, in one go, are correcting both for the local resolution and for a correct scaling factor in sharpening. But since we are transferring some information from the model, you of course need to make sure that this does not bias your density. In this case, it's just amplitude information that is being transferred, but nevertheless, it's important to see whether this affects the result. So what you see on the left, far left here is a density stretch for this helix in the unsharpened density map. And what you see here is a stretch of that helix with the wild type sequence assigned to it. And you see the B factor plotted onto the backbone of that structure. It's a residue average B factor. And what you see underneath always is the result that we obtain if we use this as a reference map to basically sharpen our original reconstruction. And what I want to pay you attention to are these two residues. So there's one phenylalanine at position 436 and a valine at position 440. So if I use this phenylalanine now and I introduce a mutation, I basically replace this with an alanine, and then I generate a simulated map from this reference structure. So that is our reference map. You see that the density at this position disappears. So what you see superposed on this structure is always the simulated reference map. But you see that in your sharpened map, so if you use this reference map to sharpen this density, the density for the phenylalanine perfectly comes back. If I do the opposite, so if I basically now take a small side chain and replace this with a very large side chain, in this case, a substitution of valine against tryptophan, then you see that there is no extra density for the tryptophan coming up at this position. That's also what you would expect, because all you do is transfer information from the amplitudes, and on top of this, these are radially averaged. But you can put this to more extreme, so you can take a polyalanine model, basically strip all the side chains off your model and generate a reference map, and then you use this reference map to scale the original reconstruction. Also in this case, you see all sidechain information coming up again. You see them a little bit attenuated because they are shown at the same threshold, and all alanine model obviously has less scattering power than a model which has additional atoms in it. But you can quantify this as well. So if I take the wild type model and I calculate the correlation, real space correlation with the wild type sharpened map, this is the profile that I get. And if I then use the wild type PDB in every case and calculate the real space correlation to the maps which have been generated using different reference density maps, you see that these curves basically perfectly superimpose. So there is no real danger of bias in this case. What you can also do is essentially choose an entirely different reference structure. So you can take a window that has structurally nothing to do with the window that you actually try to sharpen. So if I do this, in this case, you see the target window on the left here in a gray box, and you see the window that I choose as a reference in this red box and in the top view as well. You see that they are structurally unrelated, so they have nothing to do with each other. And what I can do then, what I want to show you with this, is that all that matters is that you have a correct fall-off estimation of your B factor from this reference window in order to correctly sharpen your target window. So I can use this reference window, and then by just changing the B factors of the model, I can generate a reference window with different B factors. I can choose one with a refined B factor at this position, so this will be very low. I can choose one that approximates the B factor I estimated from the target window, and one in which I have blurred it over the B factor that's actually relevant for the target window. And then you can look at the target window, and you see that these structurally have nothing to do with each other. But I can use this now. So this target window contains the same helix. And If I use this now to generate sharpened maps, then you can see if I use a B factor that is too low, then essentially I generate a result where we are running into over-sharpening, so you're starting to lose connectivity in this region. If I use a B factor that's significantly too high compared to the estimated B factor for the target window, then I'm starting to blur the density. And if I use a B factor that is close to the B factor estimated from this target window, then I get a result that really is reliable. So all that matters is that you have this fall off correct. Then there is a more severe danger of bias if you consider that you have a map, but you only have an incomplete model. That is, of course, very dangerous. So that will mean that at some point you will lose density in regions that are not explained by your model. But I want to show you that even in this case, you can, if you do this carefully, recover some of this information. Because the box that you're using to scale extends well beyond the model that you're actually using. So if you have an incomplete model, this is TRIP-V1 channel, where I now have a model only for the transmembrane region, and you see that the extracellular part actually is completely uncovered by a model. And now I use this model to scale the density locally for this structure. What you see that in the transmembrane region, you now see a lot of additional detail coming up. So you see nice helices with side chains. You see that on the top part of the extracellular region, we're actually losing density because the window does not extend far enough. But in other parts, we see additional density coming up that's in the extracellular region, not explained by a model, but approximately correctly scaled already. And then you can use this density and extend your model, use this model to this extended model to scale again your unsharpened density and continue until eventually you end up with a completed model and use this completed model to then completely sharpen your entire density map. But I want to warn you that if you do this, you should be well aware that this may introduce loss of density in your structure if you're not doing this carefully. Then the question is, how do we evaluate optimal sharpening? So when do we actually know that our map is optimally sharpened? Most of the time we look at this, that's EM, we say that looks good, but that's probably not the way to do it. What you know is that the map should provide a maximum level of detail, that's what we want to achieve, but we also know that the map should actually show expected features of macromolecular structures. And you can use the fact that that's well known from crystallography, protein crystallography, that secondary structure imposes characteristic deviations on amplitude profiles. So if you have a perfect Wilson distribution, you would have an exponential decay of your structure factors. But if you have secondary structure, that imposes, through its repetitive features, it imposes deviations on your amplitude profiles. So you basically see these characteristic peaks and troughs in your amplitude profiles. And they're characteristic for alpha helices and beta sheets. And you can now use this information to basically determine a B factor in which you are maximizing these effects. So this is just a simulation in which I take a helix that is, in which I simulate density at one particular resolution, but using various B factors. So basically blurring the density more and more. And you can see that if you look at these profiles, that they are very strong if there is basically a zero B factor, but they gradually disappear if the B factor gets bigger and bigger. And okay, it moves on. You can, of course, also do this with an entire map. And you can evaluate this again, and basically this looks the same. So you can see this trend coming up as well. You can use other ways to determine whether your map is optimally sharpened. So this is, kurtosis is a measure that has been introduced by Pavel Afonian from the Phoenix Consortium that basically looks at the peakedness of your map. And we see that this actually nicely correlates with using the secondary structure profile. So we decided to use this because, and we do this because we also need to somehow find a way to determine an optimal window size. So the size of the window that we are moving through the 3D density map. And you can do this by looking at these profiles and basically looking at the contrast of these troughs and peaks that determine your secondary structure deviations from a simple Wilson distribution. And then you can see that there is a certain window size or range of window sizes in which you maximize this. And this is the way how log scale estimates an approximate window size that's useful for scaling. And then we, once this all is set up, we're interested to see if it actually improves anything. So if you look at the original reconstruction here, this is RNA polymerase again, and I want you to look at this particular helix that is basically a slice through the density here. If we use a global B factor, we see that we increase the level of displayable information in this interior part, but you also see that some of the low resolution parts at the periphery become very noisy. If we use a local B factor estimation and scaling, so that's basically in a window estimate in a classic Guinea fashion the local B factor, we can improve this already. So you see that at least in the peripheral region, the scaling is much better, but you see that you also lose some sharpening effect in the well-resolved region. Unsharp masking is yet another way of how you can do local sharpening. That's also coming from the Phoenix consortium that is not really based on physical principles, but is an image processing tool. And you can use this too. This works. So you see that in the peripheral region, you nicely display the density, but also compared to the global B factor sharpening, that's probably close to the optimal sharpening factor in this region, you lose some information. If we use local scaling, it seems that in most parts we actually explain the density fairly well, and also in the central part we see comparable level of detail, maybe even more level of detail than in this case. These are other examples. I'll skip over this maybe in the interest of time, but one interesting one is the gamma secretase, and I come back to this in a second. But what I want to show you now is just a few examples on how this can maybe help you to improve the quality or the accuracy of your models, let's say. So this is an example using beta-galactosidase, and Tom has shown a similar example already before. This is the density as it has been deposited in the EMDB. You see that it's beautiful density, but it's very noisy, especially very noisy in the periphery. If we now use local scaling, we're getting rid of a large part of that peripheral noise. We still reproduce many of the excellent features in the density map. And if you look at the power spectrum, a radially average power spectrum of this density, then also we see that now we see a much more realistic fall off of that density. Here you see basically a flat B factor over a large spatial frequency range, and then there is some filtering artifacts already as well that come into this. But this is an example. Tom showed you an example where you can basically use the application of different sharpening factors or blurring factors to achieve a similar result, but that means that you do this with your entire map. So if you blur a map, then you will blur it everywhere. You can do this in COOD also in a nice interactive way, but the goal of this is to basically create one map that maybe reliably reproduces all the features in the map simultaneously at the correct sharpening level. So if we look at this loop region here, and we look at the deposited map and the PDB that has been deposited alongside with it, this is basically how it has been built into the density. Yeah, it's not entirely convincing, I think, that it has this particular conformation. If we use local scaling now, we can basically see that we can regenerate some of the continuous backbone density in this region because the B factor of this stretch in this particular part in a larger box will be very high. So that basically leads to blurring of the original density. And then you can rebuild the model into this density. And now the nice thing of beta-galactosidase is that there are also very high resolution crystal structures. So if you now compare these newly built conformation with a 1.4 angstrom crystal structure, you can see this is the deposited model as it has been built in the original density map, and you see in gray the crystal structure conformation of that particular loop. You see that this doesn't fit very well, but if we rebuild it into a locally scaled map that suggests a different conformation, then it seems that we are coming very close to the conformation that has been solved in the crystal structure. This is another example. This is gamma secretase at 3.4 angstrom resolution, and this is a beautiful structure which shows quite a number of N-linked glycans in that structure. So you see that this is basically a PDB model, and all the yellow ball models are asparagines at which N-linked glycans are attached. This is the density from the EMDB. So you see here the transmembrane region. You see the region in which the N-linked glycans are on the extracellular side of the membrane. And if we do now a local scaling of this map, we see that on many positions where we see these asparagine residues, we actually start to see additional density that's suggestive of disordered glycans at this position. What we did then was simply calculate a difference map between these two to localize the regions in which we see additional density. And then you see that all this additional density is located at known glycosylation sites. But in purple, you also see a few additional densities that turned up at positions that actually had not been reported to be glycosylation sites before. But if we map them to the original structure, you see that these are all protruding from asparagine residues. And if you do theoretical predictions for glycosylation sites, then at all these additional sites, you actually have predicted glycosylation patterns as well. And if you look at the density, we certainly are not able to confirm that this is the conformation of the glycan in this density, but you do see that you see additional density that is suggestive of glycosylation. These are just a few more examples. This is a particular loop region in TRPV1 channel that you see in the traditionally globally sharpened map and in a locally sharpened map, and you can see that there are some changes needed to accommodate this loop. This is another example from RNA polymerase, where in the globally sharpened map you can't see exactly how this main chain trace is protruding further. In a locally scaled map, you see that there is density coming up that is suggestive of a short helix. And if you look at secondary structure predictions, indeed, it seems that there is a predicted helix at that position that you can possibly extend. I'll skip over this as well. Just come to the last point I want to make, that such locally scaled maps may help you to build your model, but they may also help you in a very simple case of just displaying your model. Because if you have a map that varies drastically in resolution, displaying all the features that you want to display at one particular threshold level is often not very easy. That is different if you have a locally scaled map where basically you can use a single threshold to show all of these features simultaneously. And this is one example. This is again RNA polymerase shown at different threshold levels. So if you show this at 4 sigma, for example, you can see nice density for this well-resolved part, but you almost see no density for this poorly resolved part. If you want to display this more poorly resolved part, that goes to the expense of seeing the detail that you could see in this well-resolved part. If you have a locally scaled map, then you can use a single threshold, and in principle, you can show all of these features simultaneously. And that's shown in a bit more detail here. So basically, this is one of these regions that is quite poorly resolved. If we look at this at 4 sigma, where we still see many of the well-resolved features, we essentially see no density in that region that is very interpretable. If we increase the sigma, certainly that density is there, so we're not generating anything new. But if you use a locally scaled map, then you can show this at 1 sigma level. You can see the details that are present in the density in that particular region at the same time that you can display the features that are present in a more highly resolved region. This is another example for this. I'll just come to conclude that resolution variation in cryo-EM maps poses many challenges for model building and possibly also for model refinement. I think that optimal map sharpening is not as trivial as we often think, but a variation in local resolution and cryo-EM maps may require local filtering. I think that has become common practice already, but it may also require local sharpening. And I believe that local sharpening in cases can serve to improve poorly resolved map regions and aid you in model building. There are many challenges, I think, that remain, but we are working on making the tools better, and there are also other approaches that are coming up. So Phoenix, for example, just released Auto-Sharpen, and that is also able to do local sharpening. And all of these tools are freely available, so you're welcome to download them. They're also, thanks to Tom, integrated into CCP-EM, and Oscar just told me that they also had plans to put this into Symposium. With that, I'm happy to answer any questions.
Great, thanks. Right, any questions? So maybe I can start. Just a general question. I mean, the optimal sharpening, does that depend on what you want to do with it? So I guess
Probably,
different
yes.
automated model building programs may prefer different levels of sharpening.
Yes, I think it will depend on what you want to do with it, yeah. I think what I meant with optimal sharpening was just to create a map with the maximum contrast that you can have. Whether that is the best map for doing model building, automatic model building, or model refinement is a different question, I think, that we would need to investigate, yeah.
Yeah.
Okay.
Sorry.
Sorry.
The assessing the model bias introduced from the model. If I understood correctly, the model doesn't contribute phase information,
No.
right? So, was that something you were showing us to say, look, it's okay, it doesn't introduce model bias, or is this a procedure we ought to do and set up manually ourselves when using the software?
No, I think you don't need to do it. I think what I wanted to show you is that if you do this correctly, it's not a problem. If you are worried with it, I encourage you to try and do it, and then you will see that it's not a problem.
Okay, any other questions? If not, let's thank Arjen again, and we move on to